Yeah, please let me know if you get my screen. Yeah, sure. Thank you. Uh, Before we begin the modeling, I'll just briefly highlight, you might have already studied in detail about consolidation analysis. Uh, if you talk about the finite element modeling of consolidation, it is either done to understand the time required for the settlement to occur, or the time required for the excess pore pressure to dissipate. So usually in urban areas where you have the conditions or soft soil, you need to improve its bearing capacity before you construct anything on that. So that is the reason why people go for ground improvement. There are other methods as well of using certain kind of foundations where, but in certain situation the ground improvement proves to be more economical than adopting to a different kind of support system. uh, so this technique of consolidation or accelerated consolidation is done in order to increase the shear strength of the soil, and it reduces the permeability and the compressibility. So the basically, if this is your soft soil, and if you construct a building over it, over the time what would happen, because of the increased overburden, the excess pore pressure would develop and it will dissipate, and this will induce the settlement in the ground. So your buildings would occur or might develop cracks in your beams and columns. So that is the reason why you improve the ground or you improve its engineering properties of the ground before you carry out the construction. uh, just allow me to change the color here. Yeah. So once, if you construct the building without any substantial improvement and without carrying out any substantial improvement in the ground properties, so you will end up getting ground settlement, and that will impact the structural forces, or it will induce the damages in your structure. Now, what is consolidation? Basically, consolidation is nothing but compression of soil due to expulsion of water under static load. Uh, there are two conditions. One is if you have a cohesive soil. Suppose if you have a clay, which is a cohesive soil, and generally its permeability will be very low. And suppose you have a sand or a gravel material, its permeability will be high, so there won't be any problem. The excess pore pressure or the pore pressure dissipation will be quick. But in case of clay, there are two conditions, because the clay particles have the properties of cohesion, or they develop diffusion layer, and then there is a water pressure. So in order to dissipate the water, it takes a lot of time, because one thing is there is a more of cohesive force, and another thing, the permeability is very less. So as and when you add a static load, so there would be development of pore pressure, and with time this pore pressure gets dissipated, and you would be getting some amount of settlement. And you need to know what is the time required for the, or time at which my suppose say you want to start construction at 90% of the settlement. And theoretically, if you have estimated, let's say it would occur, there would be a settlement of 120 and you cannot construct your building till the settle this amount of settlement occurs. So in order to know this time, you will what we will do is we will develop this in any of the finite element platform, for example in Midas GTSNX, and then we will see what is the settlement and the time taken for the settlement. And if you see what kind of settlements occur, particularly in the soft soil, there is a immediate settlement, then there is a primary consolidation and the secondary consolidation. This immediate settlement is more of an elastic nature. This occurs as soon as you place any kind of surcharge on the soil. However, the primary consolidation is due to excess escape of pore pressure. There is a soil particle, and if you see, just let me change the color. there is a pore pressure between these two soil particles. And as soon as this dissipates, so you will get a primary consolidation, and then there is a secondary consolidation which occurs in the long run or in the long term, that is also called as creep effect. This occurs because of long term sustained load. So these are the different kind of settlement that one can expect, and we are more interested in knowing immediate and primary consolidation because that would cover maximum of the expected consolidation. And then, so what are the techniques that are employed for particularly clay soil or the soft soil? So in generally people go for if there is a ground layer, what we do is we will put a surcharge on that, and then we will have these drains. These are PVDs or plastic board drains or prefabricated vertical drains. So because of the increased surcharge load, there will be increase in pore pressure, and these will act as a escape path for the developed pore pressure. So this is one technique, and another technique is we use sand compaction or gravel compaction piles. So what we do is, if there's a ground level, we insert or we add the stone column or the sand columns here. So suppose this is the clay and this is gravel or sand. So there will be increase in the permeability for this region. So whenever you add the surcharge, the water escapes and then it gets released. So these are different ways of carrying out ground improvement technique. And for the today's work, what we will do is we have an embankment where we will do both. We will add a surcharge, that is embankment, and know the settlement behavior, and we will also do the same model by carrying out suction. Sometimes if it is not possible to add the embankment or a surcharge load, they act what we will do is we will add the suction. Suction is to take out the water from the ground. So we will add the suction pressure and we will see the settlement. So both the methods we will see in the today's training program. So without wasting time, let's start modeling now. So I think I have shared a file. Its name is suction drain.dxf. So I kindly request all of you to download that. So once you download, I request you all to open GTS-NX. Uh, yeah, I hope you can see my screen, right? Uh, shall I proceed further? So this is the once you open the GTS-NX, you will get this window. Uh, what we will do is today we will try a plane strain model. So we will click on a new file. Here you can see we'll get the analysis settings. So here what I'll do is I'll just name it as a suction consolidation. You can write your name and description is consolidation. And today we will do a 2D modeling. That's a plane strain modeling. So I'll choose 2D as an option. And then if you see the unit system, here we have kilonewton, meter, joule, and second. Because the consolidation takes time in terms of days, we add the load and we wait for certain days to occur. So what we will do is we will change this to day. So I request everyone to please make these changes. I'll repeat again. You can add the project title and then write your name, and then brief description about the today's work, that is consolidation analysis. We will select model type as 2D, and then the direction of the gravity will be y direction, and then the unit system we will choose kilonewton, meter, joule, and day, because the consolidation takes a certain number of days. Okay. And then we are not going to change any of the initial parameter or the water parameters. I'll just click on OK. So if you see now, we have this window or this work plane where we have certain grids in both X and Y direction, and you see a red arrow here. So what it means is it is the self weight defined by the system or the gravity load defined by the system. So what we'll do, we'll hide this for a moment so that your view for modeling will be very clear. So later we will see when you can activate or how you can activate this. And if you see the grid size, you can measure here using the measuring tool. If you see, the grid is 20 meter by 20 meter. This is by default defined by the system. If you'd like to change the grid, you can change the grid as well. Let's say I'll make it around 5 meter, and I'll define the number of grids in X and Y direction as 100. Okay. So now if I go ahead and measure the distance, it is 5 meter by 5 meter. So 5 meter by 5 meter. Okay. So here there are two options. You can either create the geometry of the embankment and the soil layer, but GTSNX has an import function. Okay, so I have shared with you the DXF file. So I'll open the same. What I'll do is I'll click on this file option, then I'll go to import, then I'll go to DXF 2D wireframe. Okay, so if I click on this, so I'll get an option to import both 2D and 3D. So we are working on 2D problem now. So we will select an AutoCAD DXF file. This is the same file that I have shared with you people. I'll click open. See, the now the file is now imported successfully. I'll click on apply. Now if you see, we have imported the entire geometry. Okay. Now, to for the better view, what I'll do is I'll hide the grid and also the axis and the local axis as well. So here we have an embankment, soil layer 1, soil layer 2, that is this is the clay layer which will undergo consolidation, and these lines, vertical lines that you would see, are represent the PVDs or the vertical suction drains. Okay, and there is a another soil layer over here. If you measure the distance, the total depth of the model is 15 meter and the width is 120 meter, and we have an embankment of size is 10 meter, and let's measure point and edge. The embankment depth is around 5 meter. Okay. So what we will do is now the geometry is already created. Now we need to mesh it. Okay. So before we mesh, we need to define the soil materials. Suppose we have an embankment, then we have soil layer 1, then there is a clay layer, and then there is another soil layer. So we will define the material for all of these now. So what I'll do is I'll go to mesh and then I'll select on the property or the material. So I'll go to mesh. First, we will define the material. What we'll do is we'll go from top to bottom. We will define the embankment material, then the soil layer 1, then the clay layer or the soft soil, and then another layer, that is soil layer 3. So I'll choose isotropic, and then we are defining it as an elastic. So I'll name it as embankment. We will add Young's modulus as 10,000, and then Poisson's ratio as 0.33. The unit weight be 17, and the Q naught be 0.5. And we will not change any of these parameters, thermal and damping, but we will see the porous. We'll use the default values. We'll add the saturated unit weight as 18. and then we'll add, since it's an elastic, you can add the initial void ratio as 0. We are not interested in studying anything about embankment. We will only, we are interested in analyzing the consolidation of clay layer only. And we will choose drain parameter, that is the embankment is considered to be drained, so that whenever there is a release of excess pore pressure, it will go up or it will dissipate properly. And here I'll add the Skempton's coefficient as 1, and then the permeability coefficients I'll add 0.009 meter per day. Okay, and we will add the storativity, specific storativity as 0. Okay, so I'll click on OK. So here you can see we have defined the material for embankment. I'll repeat once again the values. We will choose model type as elastic, and then we have entered the Young's modulus as 10,000, then Poisson's ratio as 0.33, and then the unit weight as 17, and the K0 value as 0.5, and then coming to the porous tab, we have the unit weight, that is saturated unit weight, as 18, and then drained parameter, and uh, we will add Skempton's beta coefficient as 1, and then the permeability coefficient is 0.009 meter per day. Okay, and just click on OK. Now the next thing is to define the material for soil layer 1. Again, we will create isotropic material, and here also we will choose elastic, and I'll add Young's modulus as 5000, and then the Poisson's ratio is 0.33 and unit weight as 18, and K0 determination or K0 is 0.5, and then for the porous we'll use saturated unit weight as 18 kilonewton, and then we are not interested in its void ratio, so we'll enter 0. We'll use drain parameters, and we will use the undrained Poisson's ratio of 0.5. So we'll go ahead with the default values, but we will change the permeability coefficients at 0.009, 0.009, and 0.009 meter per day. And again, for specific storativity, we'll add 0. And I'll click on OK. So if you can see here, the name is isotropic. We will rename it as AS1, and then we'll click on OK. Now we have defined material for this soil layer 1. Now we will define the material model for the soft soil or the clay soil. For that, what we'll do is we will add again the isotropic material, but the model type will use soft soil creep. And here I'll just name it as AC1, and then let's enter Young's modulus as 3450, and then Poisson's ratio as 0.35 and unit weight as 16, and then K0 again value of 0.5, and now we will go to the porous tab. We will enter the unit weight as 16, and the void ratio is 1.76, because the clay usually have high void ratios. We will choose, because we want it to be drained, so we'll use drain parameter, and it will have much higher, much lower permeability compared to all the layers. So earlier we entered the value of 0.009, so now we are entering the permeability much less than that, that is 0.001, and then we will enter specific tolerability as 0. Under nonlinear tab, it indicates or it establishes its behavior or the consolidation behavior. These parameters can be determined when you carry out 1D consolidation analysis. So I have the values for the time being. We'll use them. So over consolidation ratio as 2.05, and then the slope of the console line or the consolidation line as 0.313, and then the slope of over consolidation line will enter at 0.063, and K naught is 0.5, and we will enter cohesion as 10 kPa, and friction angle as 28, and dilatancy angle as 0. Okay, so I'll click on OK. Here you can see we have added soft soil creep. Okay, and now the last layer, that is the soil layer 3. Again we will go to isotropic. Here again we will define it as an elastic material. So I'll name it as AS2, and then Young's modulus I'll enter as 1 lakh or 140,000, and then Poisson's ratio 0.33, unit weight, that is bulk unit weight, as 19, and K naught again we'll use value as 0.5, and for the porous tab we'll add saturated unit weight as 19, and then the permeability coefficients again 0.86, 0.86, 0.86, and we will make the specific storativity as 0, and I'll click on OK. So any do you have any doubts till now? Like, should I repeat any of the step? If anyone can speak of, like, you guys are following, right? Uh, so shall I proceed now? Or okay, thank you. So till now, I'll just repeat what we have done or what we did. We imported the geometry, and then before we mesh it, we need to define the material. So we went to mesh tab, and then we clicked on this material, and then we created the isotropic material for embankment, then the soil layer 1, then the consolidation layer or the soft soil, and the soil layer 3. Okay, so here we have used elastic properties for the embankment and the soil layer 1 and 3, and soft soil creep material model for this soil layer 2 or the middle soil layer. Now we need to define the property for it, because we need to tell the software whether it's a 1D material, 2D material. Here we'll go to property, then we will click on this create option, and then 2D. Here, since it's a plane strain modeling, you can see here we have the option for creating the plane strain property, that is 2D. Here if you see, all the material models that we defined have come here. So what we will do is we will define the property for each of the material. Here I'll first define it for embankment, and I'll click on apply, and next for the soil layer 1 we'll use the same names so that it won't create any confusion. So AC1, this is the consolidation layer or the soft soil, and then is the last soil layer. I'll click on apply. Now, what we need to do is we need to mesh each and every of these lines or these zones. So first we will begin with the meshing of the embankment. Okay. So for the meshing, we have various tools here, 1D, 2D, 3D. So the present problem is a plane strain problem or a 2D problem. Then we will use this option called 2D. Okay, just allow me a moment. So I'll click on 2D, and here I'll use auto area option. Before that, we need to perform an intersection option here for the geometry, because before you proceed to the meshing, you need to make sure that all the zones are bounded or they are connected. So under the geometry, we have option for intersect. I'll select that and I'll select all the curves and I'll click on OK. So now we have ensured that there is no gap between the different zones, or you can see there is no gap between the lines of different soil layers. And now we'll proceed to the meshing. I'll use 2D, then auto area. First, I'll carry out the meshing of this embankment layer. I'll use size as 1 meter, and the material should be embankment, right? And then if I just click on the preview, you can see these red dots over here. So uh, yeah, you can see the red dots here. So that indicates the location of the nodes. Okay. So I'll just click on apply. You can see here now we have generated the mesh set. And if I go to this model section and expand this mesh, here we have created the mesh for embankment layer. Now for the soil layer 1, what I'll do is I'll again go to this option called 2D under mesh. I'll choose select area. So I'll choose all these lines for the soil layer 1. And now I'll again use size as 1 meter. And then the soil, this is soil layer 1, so I'll name it as AS1. And if I just click on preview, you can see here uh, apply, and then we have meshed this entire um, soil layer 1. Similarly, we will do for the layer 2 and 3. Here what I'll do is I'll again go to 2D, and then I'll go to auto area, and I'll select the lines or the zone of this clay layer or the soft soil, and I'll again enter the size as 1 meter, and then I'll choose the soil layer, that is AC1, and here I'll select the inner domain as well. And if I just click on the preview, here you can see all the zones are able to be meshed. Now I'll just click on apply. Here you can see we have created different mesh because the zones are different. And similarly, now will they carry out the meshing for this the last layer. Okay. And now again I'll use auto area option, and I'll select this region and use size as 1 meter, and then the soil layer AS2, and I'll click on apply. Now we have carried out meshing of even this layer as well. Say for instance, I want to know, here you can see if I just click on any of this mesh set, here I can see the property and the material. This is AS2, we have material and property as AS2. Similarly, AC1, that is clay, and the topsoil, that is AS1, and then the embankment. So this finishes our creation of geometry and then the meshing. Now we need to assign the boundary conditions for the consolidation to occur. For example, for any consolidation, there would be a groundwater level, and then whenever you insert the suction drains, you need to give certain suction pressure so that the water or the excess pore pressure is taken out. So we will see how you can do that. And for the present case, we have water level at the ground surface, and first we will define that. For that, you need to go to seepage or consolidation analysis, and here you can define the water level, and I'll select the top edge. Okay, so I'll select the top edge, and then name it as water level 1. Water level 1. Okay, I'll just click on OK. And if you go to this functions under analysis section, here you can see we have defined the water level now. Okay, and if I just check edit, you can see the value is 15 because the depth of the soil layer is 15 meter, which we saw. Okay, so if you see here, this is the coordinate or the center point of the coordinate, and the distance, if you measure here, 15 meters. So what we did is we used this edge which has the coordinate system inbuilt with it. So based on the coordinate system from the center of the axis, it has taken the water head or the total head as 15 meter. Okay, now we need to define the boundary conditions for the soil. So for that, what we will do is we will go to statics and slope analysis. Uh, I just want to be sure you guys are following, right? So is do I need to slow a bit, or is it fine by you? Fine, right? Oh, so yeah, thank you, Mohammed. Uh, so you need to assign the boundary condition. What do I mean by boundary condition? As a ground, you are interested in knowing the vertical settlement. Okay, so we need to restrain the movement of the base and the sides. You don't want your ground to flow here in this direction or in this direction or in this in the entire model settling in y direction, because the ground has a infinite boundaries, so your movement will be restricted after some time. So that is the reason we have defined a large boundary or the large region of 120 meter. So to define the constraints, we will click on the constraint option, and we have the auto. We will use the auto option, and we will name it as general boundary condition. So I'll click on OK. Then you can see here the nodes are now restricted in x and y direction, and here this node cannot flow in this direction, but it can vertically settle. And similarly, this side, if you see, it cannot flow in this direction, but it is not restricted in vertical direction, so you will get settlement values properly. And now we need to define the suction. Okay, so we have these vertical lines representation of the suction drain. So to define the suction pressure, what we will do is first we'll go to model option. We will hide all these mesh sets now. So if I just click on this, if I disable the mesh, so all are now, we have just hided them. We have not deleted them. We have, it is still there. I just hided them so that it is easy for me to select these lines. So what I'll do is I'll go to C page. Then I'll go to nodal head. Then I'll choose edge, and I'll choose all of these. So we have selected 9 objects. So I need to give section. So I'll give it as -5 meter. So if you talk about pressure, but the value I have given is 5. So software calculates there is a value of 5, and total pressure, if you see the it is multiplied by G, the 9.81. Uh, that is acceleration due to gravity, or you can even say -5 into 9.8, which closely it's around 50 kPa. Okay, so now the suction pressure is given as a water head. So water head into its gamma, that is 9.8 or 10. So it is close to 50 kPa pressure. Now I'll name it as suction. Suction pressure, and I'll click on apply. You can see here now there's a red dot indicating there is a certain boundary condition assigned to these edges. And I'll just again apply all the mesh sets now. And now the next step is to define the self weight. For the latest versions of the GTS NX, the self weight is already defined. That is the red dot that we saw in the beginning. So what I'll do, I'll go to analysis option and then expand the static load, and I'll just uh, we had disabled this. Then I'll just click on I'll select the static load, and you can see here the gravity load is now added. Okay, now Till now what we have seen, we imported the geometry, then we defined the material, then we gave the properties, and then we carried out meshing, and then we assigned the boundary conditions to the extreme edges and the bottom edge, and then we also applied a suction for the locations where you are planning to insert these PVDs. Okay, now the next step is to create the construction stage. For that, we will go to seepage and consolidation analysis. I'll click on the stage set. What I'll do is I'll first carry out, since there are two ways of consolidation analysis. One is for this using the suction pressure, another one is to for this adding this surcharge. So we will analyze in both the using both the cases. So first we'll define the construction stages for suction drain, and then I'll choose fully coupled stress seepage analysis, and I'll click on add fully coupled stress seepage, and then I'll click on add, and I'll define the construction stage. So I'll click on this define construction stage button. I'll get this another tab, and what we will do is we will now define the construction stage. You can see here the activated area does not have any of these mesh sets. So what I'll do is I'll click on activate. You can see there is nothing to be seen here because we have not added any data in the activation set. Okay, so what I'll do is I'll add all the mesh set except the embankment, because here in the suction drain method we are not using embankment to induce the pressure. Instead we are using suction pressure. So except this embankment mesh set, I'll add all the other mesh sets, and then I'll choose the general boundary conditions and the self it. Okay, so I'll click on water, define water level, because we have defined the groundwater level that we need to call here. Okay, so initial define the water level, and then I'll enter 1 meter, and we have already defined that function. If you remember, I'll call it here. Okay, and then I'll clear the displacement because it's an initial condition or the initial state. I'll name it as initial state, and then we need to also define the durations. Okay, so we will define the duration as 1 and this steps also as 1, and then click on the save result, and I have added generated that step. Okay, so I'll explain you what all we did. So in construction stage definition, we this is the initial state. We have activated all the soil layers except the embankment, because instead of using embankment or surcharge, we are using suction method here. So I have activated all the mesh sets for the soil layer 1, then the soft soil and the soft layer 3. Then I added the general boundary conditions, and then the self weight, and then what we did is we had defined previously the water level, we called that here. So I'll click on this define initial water level, and then the multiplication factor is 1. If you remember, we had seen a head of 15 meter in the function definition. So that function we are calling it here, adding, and then it's a initial stage. I'm not interested in any of its displacement, so I'll clear off, and then we will click on time step. So here I have added duration as 1 day, and I only need it in one step. So I added one and clicked on this save and generated that step and clicked OK. This we will save, and then we will click on new. So next step is we need to activate the suction. Okay, this is where your consolidation begins. Okay, what I'll do is I'll just activate the suction pressure. You can see now the red dots have appeared here, and then we will define the time steps. We need to activate the suction for 10 days. So, and we will see the outputs in 5 steps. Okay, so every second day we will get our output. I'll generate the steps and click on OK, and then save the step, and then I'll click on new. Okay. Here we are not clearing any of the displacement because we are interested in knowing the displacement as the suction progresses with days. Okay. Then I'll click on new. Here, once the suction pressure is applied over a time, you need to allow it for dissipation. So what we will do is we will give a levy time. Here we will deactivate the suction pressure, and then we will only allow for the soil to dissipate all the water, and here we will give more time, 180 days, and we will check results every 10 days. Okay, so then I'll click on save and generate the steps, and then I'll click on OK, save. Okay, and then close. So we have defined the suction drain construction stage here, initial, and then there is a suction, then we disable the section and we assigned a levy time. Then another construction method or another type of consolidation, instead of adding the suction pressure, we will activate the embankment. So I'll click on this and I'll use embankment. And then again, I will add the fully coupled stress seepage analysis. Here again, I'll define the construction stage. And if I just activate again, we will not see anything here. Again, the same procedure, initial, state. Here I'll activate all except the embankment, and then the general boundary condition and the self-weight. Here also we are not interested in knowing any of this displacement, and again I'll define the global water. Again we will call the function that we defined, and for the time step I'll say it is in 1 day. I'll get only one step result here. I'll click on save, and then the next step, if you remember, next step we had activated suction pressure, but in here we will activate the embankment. Okay, that is the surcharge. Okay, so we will activate the embankment, and then we need to give time. Okay, so if you remember, we had given 10 days of the suction, but embankment we will allow it to stay for 180 days, and we will check results for every 10 days. Okay, then I'll click on OK, then save. Then the next is again same, the levy time. Here we will use levy time. Here we are not removing the embankment, it will be there, and we will just assign the again or add the levy time as again 180 days and number of results to be seen at every 10 days. I'll just click on OK and save. So we have defined two two construction stages here. One is for the suction, another one is for the embankment. Now the next step is to create the analysis case. Okay, for that we will click on analysis and we'll use general. Okay, title we will give first as suction drain, and then I'll choose the solution type as construction stage. Here you can see both the construction stages have come. First, we will carry out for suction drain, and I'll click on analysis control. Here I'll activate the initial stage. Then I'll click on initial configuration and activate the stress. And then for the nonlinear case, we'll carry out the increments, and then consider the geometric nonlinearity and update the pore pressures with the deformation. We will activate this, and we will give in the loading in one increment. So we will choose the results of every increment, or if you can say I can give it in 10 and I'll give it in every increment. Results will be saved, and then I'll click on OK and apply. The next we will define it for embankment, and I'll choose embankment. Again same, the analysis control, I'll activate this initial stress, initial configuration. For the nonlinear we will add it is in 10 steps, and every increment will consider the geometrical nonlinearity, and then click on OK. So now we have defined the analysis case. The next step is to perform the analysis. I want to perform both the analysis. I'll click on OK. And it will ask you to save. So what we'll do is consolidation version. Okay. Now if you see, now it is getting executed. I already have the model uh, which is analyzed. So we will see now. See, this model is already analyzed. You can see, or we can also wait for our model to get over. It'll not take much time. You can see here total warnings are 0, which indicates that our analysis is correct. There are no errors. If you see the result, we will have, see, since we defined all the load in 10 increment, we have 10 results or 10 incremental results, and we have two analysis. One is suction drain, and then another one is embankment. Okay, we will see how the settlement occurred or started with the suction and the levy time. So if you see the initial state, and if I check the total translation or displacement in y direction, it is 0 because we have cleared all the displacement or the strain. But as the suction progresses, you can see there is a certain amount of, you know, settlement. You can see here it is less, here it is bit more. If I just show you the actual deformation, this is how it would look like. Okay, because you are taking out the pore pressure. This is the increment 1, and then the, if you see the last increment, just remember this value. I'll just make it in mm. So it's around 154 mm, and for the last increment there would be settlement of around 353 mm. Okay, and this is only in the 10th day result, because you are giving the suction in 10 days, and after that you are allowing it to drain by itself. So under the levy time, if you see the last result, so the total translation is again around around 300 mm. Okay, so if I plot the settlement graph here, I'll just go to extract, and then suction drain, and then the displacement here, translation, then for example this particular point and steps. And if I just check the table and show the graph, you can see here the settlement that is achieved. Okay, so the value is around 365, and as the levy time increased, there is again a bound back. Okay, so now the next result which I am interested to show you is the plane strain stresses, then the excess pore pressure. What we will do is for now excess pore pressure, there should be development of excess pore pressure, and then it will dissipate. Plane strain stresses, then excess pore pressure, and then I'll choose yeah, somewhere in the clay layer if I choose, and then table. Okay, so plane strain stresses, pore pressure, pore stress, yeah, just click on the table. Yeah, pore stresses, if you just show the graph, you can see there is a increment and decrease. There is a increase in the pore pressure, and then there is a decrease in pore pressure. Okay, so this is the initial, and then as you applied the section, and then it decreases in the levy time. And similarly we will see the results for the embankment. Okay, so if I expand this embankment, initially, if I just see the initial displacement, there will be nothing because we have not activated the embankment, but we have cleared off the displacement. But as you activated the embankment, you can see here there is a settlement. Okay, and if you can see, as this is pushed, and then there will be certain amount of heaving in the side. Okay, naturally, right? And then towards the last stage, we will see a total settlement of around 200 mm. Okay, so and then if you see the levy time, there will be certain improvement. So now the total settlement is around 236 mm. So if I just plot the graph for this particular node about y direction, about all the steps in table, and if I just select show graph, here you can see the settlement decreases with the time because there is an embankment, and uh, because of the embankment we can see the dissipation of pore pressure. So this is it for type of modeling. What I will do is I'll share with you people the tutorial that the same problem that we did, so that later also in case if you get any difficulties, you can refer to that, or and you can try. And if you in case if you get any doubt, you can always reach out to us and we are happy to assist you, or we can again have a meeting if you get any doubt. Okay, so is there any questions or should I show you anything else? I think I have shared the file with the professor and I'll also send it to all. Yeah, I have shared with everyone now. So you can refer to that at any point and you'll be able to follow each and every steps.